Hi, I'm Chong, and this is Justin, a mechanical engineering student from California State University, Sacramento.
So Chong, what do we have on the table here?
So what we have on the table here is PASCO Scientific's material testing apparatus. The way it works is that it has a manual crank. The manual crank is connected to an encoder. The encoder is connected to this lead screw. Connected to that lead screw is a carriage. That carriage allows you to attach a material sample piece that's attached to the force sensor that allows you to find different types of material properties, both in compression and in tension.
What's all on the table and what comes included with this piece?
Oh, very good question. So what comes out of the box is this material testing apparatus itself, safety guards that guards the machine so that the users don't have to wear safety glasses, a calibration test piece where you can use our software to calibrate the unit in order to get relatively very accurate data. And because our unit uses our passport connection, we have a USB link that allows us to connect through a USB connection to a laptop. Included on top of that, we have a single user license of our capstone software that will allow us to do the data analysis itself. And in additional, we have a starter kit that is included to allow us to allow the user themselves to start up right immediately out of the box. In addition to that, if you notice there's a whole bunch of items in front of you, what you'll notice is that we also have a shear accessory, a bending accessory, a flat coupon adapter that allows you to adapt it to the machine, and adapters that allows you to use our series of structure kits to actually do testing on our structure beams themselves. The materials that you can actually test it with, we have annealed steel, regular steel, brass, aluminum, and two types of plastic. There's a clear type of plastic. And with that, we have a set of polarizing lens that you can attach to the machine itself to see the polarizing effect on the clear plastic.
So if I were to order one of these, I get a good variety of different types of samples.
Yeah, you would get a starter kit that would allow you to start immediately.
Awesome.
So, yep.
Okay, so do we get to try it out?
Oh yeah, absolutely. Let's go ahead and remove this safety cover here and go ahead and grab a brass piece out of our bin here. And what you will like to go ahead and do is remove the spindle, spin the unit in. And then I think you might need to lower this carriage a little bit.
All right.
And then go ahead and spin the locking spindle on top of it. And while you're doing that, what I'm going to do is I'm going to put a white piece of paper in order to be able to film the with the webcam the actual breakage of the brass piece itself. This is not required. The only reason why we're doing that is so that it reduces the reflection on it. And if you notice, there's a webcam already set up pointing towards the test sample itself. So are you ready to go ahead and work out the, do a stress and strain example?
Yep, let's do it.
Okay. We already have capstone already up. First thing you need to do is go ahead and hit hardware setup to look at your hardware. And what you'll notice is that there's two icons that are in that white space. There's a USB link icon and a webcam icon, and it's the Microsoft webcam that's located right here. Go ahead and plug in the material testing apparatus into the USB link itself. Immediately, there's another new icon that is located below the USB link, and that is the material testing unit itself. There's one special other item that we need to do is that in this unit, travel going up, because we'll do a tensile test, is actually negative. So we provide a method to go ahead and switch the sign up so the graph isn't upside down. Go ahead and click on Properties, and then go ahead and say Change Sign. Hit OK. And then go ahead and close hardware setup. And then we'll go ahead and enter some formulas in the calculator itself. In reality, we have a whole bunch of workbooks that allows you to do percent elongation, Young's modulus, buckling already ahead of time. But what I want to show you is how to do this from scratch. Go ahead and hit on calculator. And within those workbooks, all of the equations have been entered in there prior to using it. You can use it in two ways, pre-packaged, or you can customize the software itself to be whatever you want it to be. What's the equation for stress?
Stress is force over the cross-sectional area.
Okay, so because we need the cross-sectional area, what happens is I have to provide you some information about our test sample. The diameter of the test sample is 3.3 millimeters. Put diameter is equal to 3.3 millimeters. What we want to do is we want to use relatively consistent units. What we're going to do is we're going to do it in meters. So go ahead and put it in 0.0033. Hit enter. Hit M for the units of meters, and then hit enter. I should provide you also the length of the test sample itself. Go ahead and do L is equal to 35 millimeters. Put in 0.035 meters. Okay, good. So let's go ahead and put the equation in for stress. Type in stress is equal to, the force is captured by this force sensor itself. If you right click and then go insert data and then select force so that the device will send the force reading to capstone, divided by, and then open the parentheses, diameter divided by 2. Where? Times pi within a parenthesis bracket. Put pi times that diameter over there. And in order to do that, scroll yourself over to the first parentheses. Within simple, you can go ahead and choose the constant pi. What's the unit for stress and SI units?
Pascals.
Correct. So type in capital P and A. And for us engineers that still works in imperial units, it would be PSI, and you are allowed to use PSI. What you just need to do is go ahead and switch the units to reflect PSI. Hit enter. And then for strain, strain equals, in order to get delta L, because delta L was equal to position, right click, insert data, and position, divided by L. And what you'll notice is that it says millimeters. So in order to keep our units the same, what we're going to go ahead and do is click on millimeters and then click on meters. And what I'm going to show you is this is the unit right out of the box without me calibrating it. So what I want to show you is how does it feel to be a brand new customer using this. Hit enter. And then what's the unit for strain?
No units.
Correct. That's a trick question. So strain has no units. Hit delete and hit enter, denoting that it has no units. Close that by clicking the calculator and drag the movie icon, which is located there, into the screen. And then go ahead and drag it to the upper left corner or right about the center and shrink that a little bit to the left to make it about a little bit less than half. Hit record movie with sync data. And what that will bring up is a selection for webcam. Go ahead and select the Microsoft Lifehand Studio. Hit OK. And what you'll notice is that now we have this webcam shooting the test sample itself. And what that will do is we'll film this actual test breakage and sync to the data for stress and strain. Drag the graph into the screen. Place it about right here. And what you'll notice is Capstone's smart enough to know that there's two elements on the screen, and it's going to go ahead and fill half the screen with the video and half the screen with the graph.
Oh, nice.
And so in this case, what we would like to do is then have stress in this axis and strain in that axis. So go ahead and click on it. You can choose a variety of data that you want to show. So go ahead and select strain, and then click that, and then go ahead and hit stress. And in this case, since we're doing stress and strain, and this material is brass, we know that strain has to be less than 1. Pan the graph over by clicking in the middle of the graph and slide that to 0. And we want to expand, go right there. And what we want to do, and then go ahead and drag that down, because what we want to do is have it 0, 0. Okay, perfect. And so, perfect. So what we're going to do next is we can go ahead and pinch and expand the graph more by clicking a spot on the bottom axis and expand it over. And then what we're going to do next is we want to 0 the sensor. So you can 0 the sensor by clicking on that 0 and 2 yellow icon arrows. And now the sensor is 0'd. So are we ready to collect some data?
Yep.
Okay, so what will happen is go ahead and hit record. And we can go ahead and collect the data for this experiment. So go ahead and crank it, and you can go as fast as slow as you want, because this is a kinesthetic experience. So if you can feel where things are at, and if you wanted to go and break it, or you want to stay in the elasticity zone or plasticity zone, you can stop and then go back. In this case, go ahead and crank it, and then crank it all the way until you break it. Perfect. So what you notice is that it then shows you data for both the elasticity, the plasticity, and the yield. And at the same time, you can see that it recorded the video with it itself. And for students, go ahead. I'm going to go ahead and hit stop, so it stops recording data. But you can go ahead and also play that back if you want to review how the testing came up. So.
Okay.
Do you have any other additional questions for the experiment?
No questions. I really like how you do the hand crank, and you can control and watch the necking yourself as you're doing it, as opposed to other options.
Correct. So another good experiment to show is if you wanted to show hysteresis, you can go ahead and have it go a little bit into the plasticity range, and then go back into elasticity and show work hardening. So, but I'll let you guys try that on your own. I'd like to thank Justin for being part of this, and I would like to thank you guys for being a part of this video. Thank you.